Hello friends, welcome to this course on convective heat transfer. In your first course on heat transfer, you would have understood that there are three predominant mechanisms of heat transfer that are studied: conduction, convection and radiation. And out of these, the most common and the most important mechanism of heat transfer is convection. You must have been told in your first course that in convection, it's actually heat conduction that happens from a surface to the surrounding fluid, which is enhanced by the movement of the fluid. So we can always say that convection is actually a combination of heat conduction and fluid motion. So quite frequently, the effect of the fluid motion on the heat transfer is termed as advection, and so convection is a combination of advection and conduction. This is about heat transfer, but while talking about convection, we normally talk about heat transfer as well as mass transfer together. So then, for mass transfer, it would be diffusion of mass accompanied by advection. So it would be diffusion plus advection, right? So let's try to just put them down. So I'll move to the whiteboard and write that. So MCL 814 convective heat transfer. Now, whenever we talk about heat, we always talk about mass also simultaneously. Although predominantly in this course, we will be talking more about heat transfer than about mass transfer, we will simultaneously also mention about mass transfer, because the same results that can be derived from heat transfer with some specific conditions can also be applied to mass transfer. So most of the time, convective heat transfer and mass transfer are talked about simultaneously. So we said that convection is equal to conduction plus advection, and this conduction, when it comes to mass transfer, would be replaced by diffusion. Okay, and since both of these are analogous phenomena, that is, conduction happens because there is a temperature gradient and diffusion happens because there is a concentration gradient, so we would normally be talking about both of them in the same fashion. So we would say that it is diffusion accompanied by advection for heat transfer as well. So we look at conduction. It's often talked about diffusion of heat. Okay. So we talk about conduction as diffusion of heat, which basically means there is movement of energy from one place to another when there is a temperature gradient. It happens in the direction of decreasing temperature. So when the temperature gradient is negative, it is the direction in which the heat transfer takes place. Just exactly as concentration. When the concentration decreases, there is a flow of the species, and therefore with negative gradient of concentration, we have mass transfer. So these two phenomena are analogous to each other, and these are actually governed by the Fourier law of conduction. Which basically says Q dot double prime, which is the heat flux, which is the heat transfer per unit area, is equal to minus K del T by del N, where N is the direction normal to the direction, the N is the direction in which we are looking for this Q. This Q dot double prime therefore is a directional quantity. So this Q dot double prime is the heat flux in the direction N. So suppose you have a surface here and the normal to the surface is N, then the heat transfer happens in the direction of N, and it will be having a negative sign because when del T by del N is positive, the heat transfer is in the opposite direction. So when temperature increases, the heat transfer is backwards, and when the temperature decreases, the heat transfer is forwards. That's why there is a negative sign. Fick's law of diffusion. Is the equivalent of this for mass transfer, which says m dot I double prime, where I is the species number, so it is species I, the mass flow rate per unit area, that is mass flux of species I, is going to be equal to minus d times del mi by del n, where mi is the mass concentration in terms of, I would say, we could actually write it as del rho I, where rho I is the mass of species I per unit volume, which is the partial density of species I. So Fick's law of diffusion can be written in terms of mass flux of species I is equal to the diffusion, the diffusivity d, and here it's a conductivity K. Both of these are properties of the medium, and del rho I by del N. So both of these have analogous looking relationships, and they also behave in the same fashion, and therefore these two are called diffusion. So this is called diffusion of heat, and this is called diffusion of mass. So you have conduction also called diffusion of heat, and therefore convection is equal to, or convection is a combination of advection and diffusion. Okay, so this is the way we normally look at it. So when we look at advection and diffusion, the governing equations for the case of convective heat transfer, the governing equation is of course the conservation of energy. And when you look at conservation of, this is for heat transfer, and if you look at mass transfer, it's actually the conservation of mass of species I. Okay, so now these are the equations that govern the heat transfer or mass transfer, but then these equations cannot be solved in isolation, because the convection of energy, basically if I talk about a surface and there is a fluid flow that is happening on top of it, so there is heat transfer from this surface to the fluid, then this, if there is no movement of the fluid to start with, then the fluid here is stationary, and the heat transfer happens by conduction to the fluid from the solid. If, let us say, the solid is at a higher temperature, T wall, let's say, is the temperature of the wall, and Tf is the temperature of the fluid. If T1 is higher than Tf, then the heat transfer happens by conduction into the fluid from the solid. Okay. Similarly, for mass transfer, if we have C wall as the concentration at the wall, or rho I at the wall is a partial density of the species at the wall, and rho IF is the partial density of the fluid in the medium, and if rho I wall is greater than rho I in the medium, then the mass transfer happens by diffusion from the surface to the surroundings. For example, if I have a salt slab that is kept here and there is water stagnating on top of it, then the salt will diffuse into the water, because the concentration of salt or the partial density of salt at the surface of the salt slab is always higher than that in the fluid that is far away from it, and therefore there is movement of mass because of the gradient in concentration of salt. Okay. So now when this happens, we have not considered the fluid motion to start with, then this entire thing happens by convection for heat and diffusion for mass. Okay. So that is already there. But when we superimpose the fluid motion, what happens? The amount of heat that is diffused into the medium at, let us say, any instant is into the fluid medium that was actually initially here, and now this is moving away. So there is a fresh medium of fluid or fresh particle of fluid that takes its place, which actually is not heated by the heat transfer from the wall, and therefore the temperature at which this fluid element reaches here would eventually be less than the temperature at which the medium were there, if I were to look at it in a very rough way, and therefore there is more potential to heat this, because the fluid is fresh and it is at a temperature closer to Tf than at T wall, and therefore it can take more energy. So normally what happens is the heat transfer gets enhanced by the presence of fluid motion. So there is always an increase in heat transfer because of the fluid motion. In the same way for mass transfer. So suppose certain amount of the salt has diffused from the surface into the fluid element that was here, and this has moved away, and another fluid element takes its place, which is closer to rho I F than to rho I wall. So there is a potential to increase the mass transfer. So advection enhances the transport. Okay, so when it is heat transport is enhanced by the presence of advection, and similarly when it is mass transport, the heat transfer is enhanced by the presence of advection, and therefore advection enhances transport. So when I talk about advection enhancing transport, then in order to quantify how much energy goes from the solid to the fluid, or how much mass gets diffused from the solid surface to the fluid, we need to also know the characteristics of the flow. So in addition to the conservation of energy or conservation of species of mass, we also need to solve for conservation of mass and conservation of momentum, because the fluid motion that is in this region is governed by conservation of mass and momentum of the fluid in general. So this governs advection, and conservation of energy or species governs the diffusion, and therefore the convective heat transfer will need to look at the governing equations of conservation of mass and momentum for the flow, and the conservation of energy or the conservation of species for the diffusion. So the governing equation for convective heat transfer would therefore not be a single equation which is a conservation of energy equation, but it's also going to include the conservation of mass and momentum equations. Right? So this is the thing that we'll need to understand. So the conservation of mass and momentum equations, if it's a three-dimensional flow, the momentum would have three Cartesian components, let us say x, y, and z components of momentum, and the mass would have it's a scalar, and therefore these conservation quantities would therefore be governed by four equations. Okay, so three momentum equations and one conservation of mass equation. If I look at it in terms of the variables that need to be solved, conservation of mass actually looks at mass per unit volume, though most of these equations are written per unit volume. So mass per unit volume is just the density of the flow, and the conservation of momentum equation would look at momentum mv per the V is not the one which cross I have put. It actually is the velocity vector. Okay, so it has to be m into V vector pi per unit volume, which will actually become rho V vector. And if this V vector is resolved in the Cartesian directions, let us say, it can be any other coordinate system also, but for simplicity we'll just write for Cartesian. It will be rho multiplied by, this will be, let us say, u is in the x direction, v is in the y direction, c in the z direction. So it will be ui plus vj plus wk. Okay, so I'll have rho u, rho v and rho w in the three directions, the momentum per unit volume, which will be the unknowns. So there will be a velocity v, there will be a density rho and a three velocity components u, v and w that come into play in this whole process. And in addition to that, because there is also a pressure gradient that drives the flow, there would also be the variable called pressure, and there needs to be a relationship between the pressure density and the temperature at which it happens. So when it is isothermal flow, if there is a temperature T, then it will be P rho T connected through the equation of state. So plus the equation of state. But this equation of state actually connects the temperature. So when there is heat transfer, this temperature also varies, and therefore the density can be varying as a function of temperature. The density can also be varying as a function of pressure, and those things are the matters of detail in fluid flow. When the density is a strong function of pressure, then we call it as compressible flow, and when the density is a function of temperature and we need to account for the variation in density with temperature, it actually becomes natural convection flow driven by temperature differences. So then the energy equation gets coupled with the momentum equations, or the equation of state gets coupled with the momentum equations. Otherwise, normally the conservation of energy equation can be solved independently of the conservation of mass and momentum equations when the density is not strongly affected by the pressure and temperature. When the density is affected strongly by the pressure and temperature, then you either get natural convection flows where the energy equation has to be solved simultaneously with the momentum equations, or you get the compressible flows where the pressure has to be specifically accounted for, and we solve for the energy equation and the conservations of mass and momentum and get the pressure from the equation of state. So this is how this set of equations get closed. So there are four equations: conservation of mass, conservation of momentum in x, y and z directions, and equation of state that govern, let us say, the advection part, and the diffusion is by conservation of energy or conservation of species. So you get the fifth equation into play, so plus energy. Okay, so if I then summarize, then advection is governed by conservation of mass and momentum and equation of state, and diffusion is governed by conservation of energy for heat transfer, and species for mass transfer. And when I say species, it's actually conservation of mass of an individual species. Okay, so the combination of these maximum of 4 plus 1 equation and this one equation would actually be about a total of 6 equations that need to be solved, and we will soon see, you might have seen it as part of your first course in heat and mass transfer, that the conservation of mass, momentum and energy are all partial differential equations, because you actually deal with dimensions, physical dimensions or spatial dimensions more than one, and also deal with time when there is a transient. So you normally deal with partial differential equations when you're dealing with these. So the advection equations are coupled partial differential equations between conservation of mass and momentum. Okay, so the mass and momentum are coupled partial differential equations. So depending on the number of momentum components that we need to look at, whether it's a two-dimensional, one-dimensional or a three-dimensional problem, depending on the number of components that we need to look at, the number of momentum equations that are solved varies, and conservation of mass. So these are coupled PDEs, and the momentum equations are non-linear. This is something that we might have talked about in our earlier course. We'll be looking at it when we look at the governing equations. And the conservation of energy and conservation of species, the diffusion equations, these are usually linear so long as the temperature does not affect the conductivity or the diffusivity. Then the equation remains linear in T or rho I. Okay, and but the velocity components that are required in order to quantify the advection come from the coupled nonlinear partial differential equations, and therefore the overall system of equations becomes coupled partial differential equations which contain nonlinear equations, right? So the system of equations is actually quite difficult to solve analytically, and therefore quite frequently the method in convective heat transfer is to simplify many of these equations. So various degrees of simplification of the governing equation become necessary when we actually deal with the governing equations of convective heat mass transfer. Okay, so when we talk about simplifications, what are the kinds of simplifications that we look at? One thing that I already talked about is to look at whether the problem is steady state or transient. In convective heat transfer, the first course that we are now studying, most of the problems we would be dealing with would be steady state, and we normally do not worry too much about transients in the standard cases that we study in a course. But then one of the simplifications that we do is steady state, which most of the time we try to use. But in problems where the transients are important, we'll also need to look at transients. So this is one. So if I take a steady state approximation, then I have already dropped one of the independent variables in a partial differential equation. So the dependence on time, whether it is there or not, is decided by this simplification. The next is dimensionality of the problem. Okay, this dimensionality basically talks about 1D, 2D or 3D. So just like we saw in conduction heat transfer also, whenever the gradients in a particular direction predominate over the gradients in the other directions, then the dimensionality of the problem can be reduced to, because otherwise, in strictly speaking, all problems in nature are three-dimensional. But then, in order to simplify the equations, we may be able to drop one of the independent variables and solve it in terms of the remainder. So that makes the problem reduce from 3D to 2D, or sometimes from even 2D to 1D. So if you remove conditional independent variables, so you may remove y and z, and the problem becomes variable only in the independent variable is only x. Then it becomes an ordinary differential equation. Sometimes it also happens that there is a similarity, that is, the temperature distribution, for example, may look in a particular shape, and that shape varies with the other direction. Say, for example, t versus y has a certain shape, and this just has a scaling factor as you go with x. So if you divide it by the scale factor, then the temperature profile with y at all x values will collapse to a single profile. That is called similarity. We'll be talking about that when we come to the topics. When I get similarity, then two of these variables can get coupled. For example, x and y can get coupled. So you can say some combination variable eta, which is a function of let's say y divided by some function of x, and this entire equation can then be reduced to one in the variable eta, where the x and y combination is getting absorbed through this kind of function, and that can be done when the problem has a certain property. Okay, so these are the kinds of simplifications. We will come to that when we actually solve the problem. So we are actually dealing with simplifications. So you can reduce to steady state versus transient, and you can reduce the dimensionality from 3D to 2D to 1D, or you can also do similarity. Okay, so this is another simplification. The other kind of simplifications that can be done is also, for example, boundary layer approximations. Okay, so all of you would have heard about boundary layers in your previous courses in heat transfer. So boundary layer is a thin region near the solid boundary, which is strongly affected by the gradient. So suppose there is a flat plate over which there is a flow that is happening. There is a thin region near the flat plate which is dominated by the effects of the presence of the plate, and the rest of the region, which is but this is just a few millimeters from the plate, and the rest of the region around it is unaffected. So quite frequently we focus on the phenomena in this region in order to quantify the convection. And in such a case, we take this approximation that this delta, which is the thickness of the boundary layer, is much smaller than this x. So delta being much smaller than x, and correspondingly the velocity component in this direction being much smaller than that in this direction. So let's say v is much smaller than u. This kind of approximations are commonly used in order to get rid of some of the terms in the differential equation, and that results in a simpler differential equation to solve. Okay, so that is another kind of simplification. So these are the simplifications that we do in order to make the problem more tractable and solvable. And after doing that, you end up getting the, either we reduce the PD to an OD, like it happens in the case of similarity solutions or in the case of one-dimensional problems. Okay, so there is a case of PD getting reduced to OD, or at least the dimensionality getting reduced from 3D to 2D, or to 2D to 1D, 2D transient to 1D transient. Therefore, there is a reduction in the number of independent variables. So the problem becomes a little bit more simpler to solve, track and handle. Okay, so or reduction in dimensionality. Okay, so this is something that is commonly there in the problems of convective heat transfer. So one thing that we always need to do when we study convective heat transfer is to understand the governing equations and their characteristics thoroughly, so that they will be able to conveniently and comfortably do these simplifications of the equations before we get on to solve it. This is required irrespective of how you are going to solve the equation. You need to understand the behavior of the governing equations and the simplifications that they lend themselves to in the case of specific problems, so that when you solve the mathematical problem to get the distributions of velocities and temperatures which are necessary to quantify the effect of the flow on the heat transfer, we need to do these simplifications. Okay? We'll get to that when we look at the methods of solving the problem. Now, once you have solved and obtained the solutions of these, basically you get density U, V, W, T or rho I. All of these variables, they come out in the form of functions of X, Y, Z and T. So you get density as a function of X, Y, Z, T. So you either get a closed form equation which gives density as a function of X, Y, Z, T, or when you have numerically solved it, you get at different values of different locations X, Y, Z and at different times T, you get values of rho, and similarly U, V, W, T and so on. So using that, what do? So we again go back to the fundamental expressions that we started with. The convection of heat usually is represented using the Newton's law of cooling, which says that the heat flux due to convection, that is the heat transfer per unit area, is going to be proportional to the temperature difference between the surface and the fluid, and the constant of proportionality is called H, which is termed as the heat transfer coefficient. Okay, so you should remember that this is an empirical observation that in the times of Newton, which was about 400 years ago, when Newton observed that wherever there is a fluid flowing adjacent to a solid, the heat transfer rate from the surface to the fluid is usually proportional to the temperature difference between the solid surface and the fluid, and therefore he characterized it using a heat transfer coefficient H. And even today, when we study convective heat transfer, this heat transfer coefficient H becomes a convenient parameter to represent the effect of convection on to compute or quantify the heat transfer rate. It's always convenient to reduce the information that we got from the numerical solution or analytical solution of these differential equations to calculate the value of H. So how do you do that? So let's go to the next page and see. So suppose I have a surface and the surface temperature is T wall and the fluid is at Tf and there is a flow. I need to quantify the amount of heat that goes from the solid surface to the fluid, and on this side it is H times T wall minus T fluid. But from conduction equation we know that this heat that is coming to the surface from interior of the body is coming because of conduction through the body. So we say that that is equal to minus K del T by del N in the solid, and at the surface when we look at it, usually the fluid motion is at the same velocity as the surface at the surface because of the viscous action and there is no motion. So the first layer of the fluid that is there would have only conduction in it. So we can also represent it as equal to minus K del T by del N at the wall and in the fluid. Okay. So on the solid side you have, so if I plot the temperature profile on this side, say for example okay, so it's, suppose this is T solid, okay, from T solid the temperature, let's say the solid temperature is uniform, and because of fluid being present it varies, and it let us say goes to the T wall here, okay, and so there is a temperature gradient near the wall, and that gradient can be quantified by this term, and this would be equal to the term on this side. So if I measure on the fluid side, there will also be again temperature variation. So finally it goes to Tf, and this is T wall. So the difference between Ts and Tf is what is driving the overall flow, and at the surface if I equate the heat coming from the solid in interior of the solid to the one that is going out, then I can actually quantify it using this K del T by del N at the first layer. So it is K del T by del N at the wall in the fluid would be equal to this. So if I write minus K del T by del N, if I write only for the fluid, at the wall is equal to H into T wall minus T fluid. This is the way we write it for the convective heat transfer. Now the gradient of temperature at the surface is obtained by solving the flow energy equation in the fluid. So you get let's say along this vertical line you get temperatures at different locations, so you can plot that and get the gradient of temperature at the surface in the fluid side. That will give you this quantity, and conductivity of the fluid is known to me. So this is conductivity of solid and this is conductivity of fluid. I know the conductivity of the fluid, so I can, and the T wall can be measured and T fluid is known, so you can actually get the value of H. So this H is an indirect parameter that is obtained by solving for temperature as a function of this coordinate n. So if that coordinate n is x or y, so this will be del T by del x or del T by del y, which can be obtained from the solution that you get of temperature as a function of x at this location. So the heat transfer coefficient can be derived out of that. In the same way, the mass transfer coefficient Hm multiplied by rho I wall minus rho I fluid can be written as equal to minus d into del rho I by del n. So this is the d is the diffusivity of this fluid, okay, so diffusivity of species I into the rest of the fluid, and this is rho I by rho n. So if I solve for rho I by using the species equation at different locations, then I can get the del rho I by del n at the fluid surface, and in the same way I equate these. Okay. So this mass transfer coefficient and this heat transfer coefficient, therefore, are composite parameters which hide a lot of information inside them, and they have to be obtained by the understanding or the knowledge of the mechanism by which the heat transfer or mass transfer occur in the presence of advection and diffusion. So that is the understanding with which we solve for these parameters and get the heat transfer rate or mass transfer rate. So as I said, Newton's law of cooling and Fick's second law, as they may call it, which basically says mass transfer per unit area, mass flux of species I at the surface is equal to Hm into rho I wall minus rho I fluid, which is the Fick's second law. Okay, so these two laws, which are very simple empirical relationships, they are normally invoked in order to absorb the effect of whatever we solved from the complex governing equation solutions that we got here to represent the effect of those on the rest of the heat transfer process. So the heat transfer rate or the mass transfer rate are calculated using the Newton's law of cooling to use in the various heat balance or mass balance calculations. Okay, so this is the way it goes. So you have governing equations, which are complex differential equations. You simplify them, you solve them either analytically or numerically, and get the temperature distribution or the mass fraction distribution or the partial density distribution. And using that, the gradient of that at the boundary, you evaluate the values of heat transfer coefficient and mass transfer coefficient and use that. Now, these heat transfer coefficients and mass transfer coefficients vary substantially with the kind of configuration that you have, with the kind of fluid flow that you have, with the kind of geometric dimensions that you have, because it's a parameter that is dependent on the fluid flow and the fluid properties, and it varies with both of them. Okay. So using that, you will end up getting the different kinds of things. Now, we also said that the problems get different levels of complexity when the temperature affects the density or does not affect the density, and so on. And the fluid motion also has different extents of complexity. So convection, both heat and mass transfer, is classified as natural versus forced convection. So natural convection is where the motion is entirely driven by the temperature gradients in the medium or the concentration gradients in the medium, because of which the fluid motion starts happening. Okay, there is no external driving force on the medium, but the medium starts moving because of the density gradients that are inside the medium, which is caused either by temperature gradients or by concentration gradients or both. In such a case, it is a natural convection, and forced convection, by contrast, is those fluid motions that are actually caused by an external agency, like you have a fan or a pump or a blower that moves the fluid, and because of that there is convection. So this is one classification that we normally have, and as I said, in natural convection you need to have the temperature coupled with density and therefore affecting the fluid motion. So the energy equation is coupled with mass and momentum. What does it mean? You cannot solve the mass and momentum equations independently of the energy equation, but they have to be solved simultaneously. So that is what happens in natural convection. Whereas in forced convection, because the fluid motion is not driven by the energy equation, the fluid motion, which is mass and momentum equations, can be solved independently. So this is a decoupled system. So forced convection problems are easier to solve than natural convection, because you can solve for the fluid flow independently and get the velocity and density distributions and use that as an input to solve the energy equation, which is linear. Okay, so that is a simpler thing that happens, but in natural convection the coupling is important. In the same way, for mass transfer, instead of temperature, the rho I would be coupled with rho, because the concentration gradients determine the density at any given location, and therefore the density gradients drive the flow. So the rho I becomes coupled, so the species equations become coupled with the mass and momentum equations. So this is natural versus forced convection. Then you have internal and external flows. So these are different categories of flows. Internal flows are where the flow is bounded by a solid surface all around. Say, for example, the flow through a pipe. Okay, so when there is a flow that is inside a pipe, it is bounded by solid on all sides, and therefore on all surrounding boundaries except in the flow direction, of course. So this is a bounded flow, and that has a different set of characteristics and different behavior. Whereas external flows, there is only one solid surface and the rest of the fluid is over the solid. So maybe, let's say, there is a rod or a cylinder over which the flow is flowing. So except at the location where the cylinder is present, the rest of the extent is large, and there is something called near wall and there is something called far field, which can be defined for this, in contrast with the case of internal flows, where there is nothing called far field, everything is bounded by the boundaries, right? So the way in which these two kinds of problems are treated are entirely different, and that gives rise to the external and internal flows. And in both external and internal flows, you can have natural convection and force convection. You can have internal natural convection, internal force convection, external natural convection, external force convection. So this is another kind of problems that we commonly deal with. A third kind of classification that happens with this is the laminar and turbulent flow. Okay. So in laminar and turbulent flow, basically we deal with flows of different nature. In laminar flows, basically the flow is dominated by viscosity, and therefore any disturbances that are introduced into the flow, they are completely consumed and mitigated by the presence of viscosity, so the flow remains smooth. Whereas in turbulent flow, the disturbances that are introduced to the flow, either because of by the surface or because of the incoming flow having such disturbances, because of maybe it is driven by a fan which is causing the disturbance and so on. Any fluctuations that are introduced in any of the variables into the flow, in the case of laminar flow, because the viscosity is present, it damps out all of those and the flow becomes smoother. Whereas when the flow is not stable enough, the viscosity is not strong enough to damp out those, then these oscillations grow and the flow becomes chaotic, and eventually it's called turbulent flow. Okay, so this is something that one might have always observed. When I open a kitchen sink tap or a wash basin tap with low flow rate, the flow looks smooth and neat. But when the velocity is increased, or when the pipe is opened, when the tap is opened wider, then the flow becomes actually more turbulent, as you can see, more disturbed, right? So this is something that is two different classes or categories of flow, and they have entirely different way of behavior, and therefore the governing equations for the turbulent flow and the laminar flow, strictly speaking, they are the same, but one tries to look at an additional set of parameters or equations that characterize the presence of turbulence in a flow, and therefore the turbulent flow would require a different set or a different kind of treatment when we solve the equations. So you can have external, internal flows which can be laminar or turbulent. You can have natural convection or force convection which can be laminar or turbulent. So you can have various combinations of these. Okay. So these are the other class of problems that come from conductive heat transfer. Last but not least, it is single phase versus multiphase. Quite frequently we deal with two-phase systems, and with or without phase change. Okay, so you can have simple two-phase flows, for example, air carrying dust particles or liquid particles, or liquid carrying bubbles of air or things of that kind. So that's a single phase, that's a multi-phase flow where one medium does not get converted into another. So these are dissimilar materials. But you can also have boiling or condensing flows. Say for example, liquid water boiling over a surface of hot pipe which is carrying combustion gases, or say things of that kind, what happens in a power plant boiler, for example, or condensation, what happens in a power plant condenser, where the steam comes and condenses on top of the cold tubes that are carrying cooling water inside them. So this is where a phase change is actually happening. So when there is phase change happening, you have one set of complexity. When the phase change is not happening, you have another set of complexity. So you have multi-phase flows, and convection can be happening in single phase flows where there is pure liquid or pure vapor flowing, or in multiphase flows where there are mixtures of solid, liquid, vapor phases flowing, and there is conversion from one phase to the other or no conversion from one phase to the other. So these are the different kinds of problems that we will normally be dealing with in convective heat transfer or convective heat and mass transfer. I'll close this lecture with the method of problem solving in convection, so that we get a feel for how we are going to approach this course. So we can say problem solving in convection. So you have what is called the classical approach and what is also the modern approach. Not that modern is always better than classical, but modern easily is more powerful than classical because of the new tools and software and computers that have come in. But the classical methods basically dealt with simplifications of governing equations, and once you have done the simplifications, it also dealt with normalization or non-dimensionalization. So non-dimensionalization of governing equations becomes interesting because suppose I have a problem that is solved for flow through a pipe which is 2 centimeters in diameter, and I now want results for a pipe which is 5 centimeters in diameter. So can I use the results that I got for the 2 centimeter diameter pipe for the 5 centimeter diameter pipe? The answer is yes, when I have solved the problem in a non-dimensional form. So the solution U by, let us say, U max or U mean is available as a function of, let us say, R by the capital R. So this is a non-dimensional radius of the pipe and this is a non-dimensional velocity of the flow. So if I have the solution in this form, then when the non-dimensional parameters corresponding to one flow are matching with the non-dimensional parameters corresponding to the other flow, the flow mechanism being the same, I can use the result that I got for a 2 centimeter pipe also for a 5 centimeter pipe because it is non-dimensional. So this non-dimensionalization is a very, very powerful tool which has been used in the classical methods in convective heat transfer, and therefore we need to also understand and follow that. Then solving the problems using various kinds of approximations, so boundary layer equations and reduction to 1D, 2D, 3D, steady state, transient, etc. All of these simplifications that we actually talked about, these actually were used in the classical method to reduce the complexity of the equation so that you can either solve it analytically or if the analytical solution does not exist, because this is a rare case where analytical solution would be feasible. You try to do the separation of variables and solve things and all that, but it's more commonly feasible in conduction heat transfer problems. But in conduction heat transfer problems, the analytical solutions by separation of variable method and so on is a little bit more complex and it's rarely done. Rather, it is numerically solved, particularly when you are able to reduce the partial differential equation to ordinary differential equations in the case of similarity methods. You also use what is called the integral approach. For example, if I have a pipe through which there is a flow that is happening, then what can be done is to look at r and z as two separate coordinates and look at the velocity as a function of radius as well as actual location. But it's also possible to look at the integral of the velocities or the mass flow across every section and look at it only as a one-dimensional problem in z of the mean velocity or the overall mass flow rate at any given section. So this gives you what is called an integral approach. You integrate the flow in the radial direction so as to get what is an ensemble of one cross section and use that which is varying with the axial direction. So the problem gets reduced in dimensionality to 1. So this is used. This is also used in external flows where you actually integrate things across the boundary layer and say that the variation and in the x direction is taken into account, but what is across the boundary layer is integrated. So this also leads to another simplification and usually leads to possibility of simplified analytical solutions for the convection problem. So all of these are the methods that you normally find in classical convective heat transfer books. Okay, but the modern method is actually capable of solving the full Navier-Stokes and energy equation or species equations using CFD, what is called computational fluid dynamics, or sometimes referred also as computational heat transfer or computational heat and mass transfer. So basically CFD is a name that is given to something which also encompasses CHT and CHMT. So basically you have computational software which are capable of solving these full Navier-Stokes and energy equations by specifying the domain of your interest and the mesh and governing equations and boundary conditions, and they can solve the entire equation. So here also these simplifications would come in handy if you are able to reduce the problem from a general three-dimensional case to a 2D or 1D case. Then the effort of computation that are required in the CFD also decrease substantially, and therefore you will be able to get the solutions faster. And therefore we need to work with a combination of the classical method and the modern method so that we can get the solutions more easily. But then this CFD provides you with a complete alternative method to whatever we learned here, but then not necessarily a substitute, because the flow and the mechanisms of convection are better understood by looking at this. This gives you a lot of numbers and which can be processed and made into colorful plots, but then the insight still comes from the understanding that happens here. So in this course we'll take a combination of the classical and the modern approaches. Predominantly we'll remain classical, but we'll also show how the modern approach can augment the capabilities of the classical method, because the classical method was developed when the digital computers were not powerful. So if you look at most of the references that come in the textbooks of convective heat transfer, they would all be dated in the 1980s or before, and whatever came after the 1980s, there are not too many results of the kind that you'd find in the convective heat transfer classical textbooks, right? So much of this that we see are results that were from 1950s, 60s and 70s, and maybe partly 80s, but after the 80s these actually fell out of favor, and most of the work actually focuses on numerical and computational methods. But then unless the understanding of this is strong and clear, the use of this actually becomes very inefficient, and therefore it's always required to study both of these in tandem. So even a modern course in convective heat transfer treats the classical approach as the mainstay and the modern methods as a supplement. So that is exactly what we will be doing in this course also. So we'll be talking about derivation of the governing equations and simplifications of the governing equations, normalization of the governing equations, and applying the boundary conditions, and then solving them using the classical methods. So if there is a similarity approach possible, look at the similarity approach. If there is an integral approach possible, look at the integral approach. And then we also look at the modern numerical method to solve the same problem and look at the results of the modern numerical method in comparison with whatever we have done using the simplified methods of solution. Okay, so this is basically the gross introduction to what we will be dealing with in the course on convective heat transfer in this semester. Right. So with this introduction, I'll stop the first lecture. In the next lecture, we'll start with the derivation of governing equations in a more generic fashion, and we'll also try to look at the normalization and looking at the non-dimensional parameters in the next lectures. So we'll stop this lecture here.